So, welcome back to another class on speech signal processing. Specifically, now we are looking at deep learning methods. We also looked at some architectures like the feed forward, then the recurrent neural networks. And then we came to something called sequence to sequence modeling, and of course, convolutional neural network. Then we came something to sequence modeling. And one of the issues with recurrent neural networks, even if you have putting the LSTM cells inside it, is the fact that it is sequential. It has to first process the first data, which is if you are talking about sequence of words, the first word before you can feed the next word. And then after you have finished processing the second word, then only you can feed the third word. So, each word has to be fed one after the other. It has to wait till the previous word has been processed, and then only you can put the next word. Okay. So, this actually slows down the training process, and therefore, it is very time consuming. So, people have started looking and actually have come up with interesting ideas of whether we can modify this and somehow parallelize the whole idea, right. We still want to do sequence to sequence, but can we avoid the recurrent neural networks? One way to, but what are the advantages of recurrent neural networks? It has some idea about the history. It knows what happened before if you are only looking from left to right, or if you are looking from the other direction, it knows what happened in the future, and therefore it is able to predict some previous words. Okay. So, it has some advantages, but it also has these disadvantages, right. And therefore, one of the first intermediate step, actually I would say, which was there for about a few months before something called transformers, which we discussed last class, is the convolutional sequence to sequence. So, there if you look at the convolutional neural networks, we have discussed that essentially they are at each layer they can parallelly process the data, simply because the kernels are fixed, and therefore we know how to multiply, and even if you do the shifts, we can parallelly mirror the data and allow the kernel to take different parts and simultaneously do the calculations. Okay. And therefore, at each layer we can parallelly feed the data till the that layers calculations are all done, and then we can go to the next layer. So, we can actually parallelize to a great extent as opposed to recurrent neural networks, where for example, if I have 10 words, right, I have to feed one word at a time till the 9th word is finished. I cannot do the 10th word. Okay. Whereas here we can feed, if I am looking at 1D convolution, I can feed the 10 words, and the different feature maps or different filters can actually go through parallelly with all of them. Okay. So, after that came this idea of transformer, which we have started discussing last class. And essentially a transformer is also an encoder decoder network. So, this is the encoder of the transformer. We will come to some of the details. This is the decoder of the transformer, and like we said in the recurrent neural networks, we could have multiple layers. In the encoder itself, we can have, instead of only one hidden layer or one recurrent layer, we can have 2 recurrent layers, 3 recurrent layers. Similarly, in the decoder also I can have multiple recurrent layers, and usually when we stack them, when you have multiple layers, that is where the idea of deep comes in, right. We usually get good improvements in performance, right. And so, here also there will be multiple layers, right, and we tend to call these as blocks rather than layers, because within each layer we actually have 2 or 3 sub blocks that are there. So, it's a little complicated, but the intuition is very simple, and that is what I was talking about last class. So, I think this is one of the most, I should thank Matilda, my student, who prepared this particular figure, right. You will not find it elsewhere. So, which is very informative. So, remember, the whole idea is that I am trying to look at the context. I want to look at all the in a recurrent neural networks, either from left to right, we are coming from left to right, so the previous history is there, or when I come from right to left the other direction, I have in the other direction, right. So, we want to capture the context, we want to see the similarity or what all information is there in the previous words one, right. That is the main advantage, right. And convolutional sort of captured that by using these filters, and we had multiple layers, so that the context became bigger. But now the self attention that transformers, so the first paper was by attention is all you need is the name of the is the title of the paper. So Vaswani and many other people contributed to this work. It's from Google, and essentially what they are saying is, if I am interested in a particular, let us say, again let us go back to word embeddings, it can be even MFCC, ML filter bank, some sequence of vectors. If I am looking at a particular vector, let us say the tth vector, I am going to look at its similarity with other vectors, which means I am looking at the context. How similar, if I am looking at as a word, right, fourth word in a 10-word sentence, how similar is it to the third word, second word, first word. That is what we mean by capturing the context, right. In a recurrent neural network, it went through the the hidden layer, and the output of the hidden layer was fed as an input to the next layer. So that's how you are giving the information of the previous word into the recurrent neural network. Similarly, when I go to the third, the output of the second has to come, and the output of second already has captured the output of the first and the input of the second, right. So therefore, there is some history that somehow we are capturing in this transformers. This is done through what we call self attention. Okay. So, the beauty is now it is actually looking at all of them. So, if you look at left to right or right to left, in the left to right first, it does not look ahead of it. So, we have to look at in the other direction and come, right. And if it is a very long sentence, the first and the last words, if you look at the middle word, are going to be less influenced by what is happening. Okay. In self attention, this is not a problem at all. So, it has even better advantages than a recurrent neural network. Okay. And so, I will discuss how they look at the similarity between these different embeddings. So, they simply look at the inner product or the dot product, right. So, how similar? So, last class I talked about dot product. If the dot product is very high, that means cosine value is very high, which means theta value is very low. That means the angle between the two vectors are very small. That means they are very similar looking vectors. If it is very low, that means cos 90, right, it is closer to pi by 2. They are almost orthogonal. Therefore, the vectors carry very little information about each other. So, if I look at the projection of an orthogonal vector on the other vector, it will be 0, right. It has no information in the other direction, right. So, therefore, we are looking at inner products, and that is also or the dot product. Okay. And what we do is now we in self attention, it is little confusing, but if you look at the idea, the terms query key and values will become easy to understand. So, let me say that t, that small t that I am looking at is, let us say, fourth word. So, how many third word, 1, 2, 3, 4, 5, 6 words are there. And I am looking at the third word. Let us say this is a 6-word sentence, right. There are 6 words, and I am 1, 2, 3, 4, 5, yeah, and I am looking at the third word, right. Now, that is the third word, when I am starting out, these are my embeddings. So, let me call them as the embeddings, whatever E1, E2 or 3. But I will also copy it, forget about this matrix, that is important, but not to confuse you, we will ignore it. So, we will call that also since they are exactly same, I will call this as V1, which is the same as the first word embedding, V2 which is the second word embedding, V3 the third word embedding, V4 the fourth word embedding, V5 the fifth word embedding, and V6 the sixth word embedding. So, I have just, those are just capturing the embeddings. Now, I also want to see the similarity of the third word, if I am interested in the third word for the time being, with the second word through the dot product, with the first word through the dot product. How do I do that? So, what I do is I am now interested in the third word. So, I will call that as a query. So, this Qt is now T is 3, right. So, this also becomes, so the third embedding also becomes the query vector. So, this is the query vector. So, I am trying to find out with respect to the third word the dot products with all the other vectors in this sentence, right, all the other words. So, I look at the query of the third word and I call the first word. Now, I am comparing this third word or trying to find out how close or similar in terms of dot product to the first vector. So, I will call the first vector as a key, first key, or the second vector as the second key, or I can go back to the third vector, self similar, how similar is it to itself, right. So, qt with kt, right. So, that will be all identical, right. So, it will be 0, it will be falling on top of each other, right. So, then fourth, fifth and sixth, right. So, the query is the particular vector with respect to whom I am trying to find the similarity of all the other vectors including itself, and so we find a dot product. Okay. So, this is a dot product of the vector with itself. Okay. So, now I will get some numbers here. Okay. But I am going to interpret these numbers in slightly different way. I am going to give them as weights later on, we will see what they are. So, I am going to make sure that I take all of these and basically make sure that they, I normalize, so that when I add them up it becomes 1, and each one of these guys are going to be some number less than 1. That is the basic idea of this normalization in softmax. Okay. So, now alpha T1 is the dot product, how similar, but I am normalizing, so it will not change, it is all scaling and so on. So, the relative things impacts do not change. So, wherever I had a high dot product, that means they are very similar, the weights will be very high, and wherever it is low, it is going to be low. Obviously, the dot product with itself is going to be a very high quantity. Okay. But I have to see what were the other guys that were very similar, and I am trying to normalize, so that I get the weights to lie between 0 and 1. Okay. Now, I do one thing that previously we were never doing, which is that I take this vector, this embedding that I was talking, which is what I am calling as value. So, V1, V2, V3. So, this is the first embedding, this is the tth or the third embedding, this is the, let us say in this case 6 words are there, this is the last word embedding. So, this is the sixth embedding, right. Now, what I do is I take a weighted, so how did the third vector, third embedding look with the first embedding. So, that weight I am taking weight, so if it is high, then I will take a large, V1 will contribute a lot. If it is very small, then beta will become very, very small. So, the sixth word will contribute very little, and the third word will go as it is, even that is going to get weighted. Obviously, it is going to get some larger weight because it is a dot product with itself. Okay. So, the others will generally tend to be smaller, but they will also give non-zero contributions, right. So, now what happens is, ideally Vt was the original embedding. Now, I am perturbing that embedding so that it shifts slightly towards the context in which it sees the other words. Okay. So, therefore, these other words are influencing it to move slightly. You remember, all of these are going to lie in a multidimensional space. So, all of them are going to move it to some more semantically or more informative space. That is the basic idea of self attention. Okay. So, if you remember this, it looks complicated. This is the idea of self attention, and we are going to do self attention for. So, I will do it for OT, like that I do for the first one, O1 will come. So, when I do the first one, O1 will come, the second one O2 will come, the third one O3. For each one of them I have to do this operation, right. So, when I look at O1, the query will become Q1, right, and so Q1 with K1 will be very similar, Q1 with K3 will be very slightly, may not be similar, Q1 with K6, the sixth query, sixth key will look different. So, I have to do O1, O2, O3, O4, I parallelly can do. Can I do it parallelly? Yes, I can do it parallelly, because I can copy this, and now for the first one, let us say this was for the third one. So, here Qt becomes 3. So, it will become Q3, 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 and I am going to compare with all of the vectors K1, K2, K3, K6, right. Similarly, if I am doing for the first one, Q1 will come here, but K1, K2, K6 will remain. Again, all these operations, there is no dependence from the previous or the past, all of them are going parallelly, right, it is just a parallel product, right, and all of them are just, once I come out of the normalization I am going to add. So, this whole step can move parallelly. Similarly, I can parallelly go and get O1, parallelly go and get O2, parallelly go and get O3, parallelly go get O4 and sorry and O5. So, now not only am I able to parallelize, this self attention is even better than recurrent neural networks. Why do we say that it is even better than recurrence? Because in recurrence it is going through this complicated LSTM cells, the output of it is fed through the weight matrix which is learnt, of course, then it is going, so it is going through so many hoops. Here directly, and so remember that when we look at 10th word, the effect of the first word is very, very small. So, if you recall, we have actually as an illustration, this is not typically what we happens, but it is more illustrative. So, this one is telling you that as I progress, what time is it, the contribution of this at O5, what is the dark black or something, time is green, right. So, what and time are very important, but because of the recurrence relation, the black and the green contribute very little to the last guy, right. So, even though we will then take care of use LSTMs and so on, essentially as we go progress larger distance between the two words, the effects in general are not that dominant. Okay. On the other hand, this is not an issue with self attention. Why is it not an issue with self attention? Because however far you are, I am treating, so even if I have let us say 10 words here, okay, and I am looking at the first word. So, however far you are always looking at the inner product. So, it is not going from the first to the second to the third to the 10th. It is directly saying from the first how is it similar to the 10th, from the first how is it similar to the 9th, from the first how is it similar to the 8th. Each one of them are equally important because we use the same operation of dot products to find the similarity of the first vector with all the other vectors. So, with the first vector, irrespective of however far the other words are, even if it is 10 words away, it will have the same influence as the next word, right, because we are giving equal we are taking dot products and looking at the similarity and which one is going to have which use for it, right. So, this is basically one big advantage of self attention, that the distance between words whether it is the next word or 10 words up away, all of them have the same influence on this particular guy. Okay. So, that is the good part of self attention as opposed to recurrent neural networks. But now you can see, you should anticipate one problem. What is that problem? Because I am just treating all vectors the same way, whether 10 words apart or 2 words apart, whether it is to my left or to my right, I do not actually capture any of this information. Why? When I am doing this, let us look at the third word. So, t equal to 3 here. So, I am going to call the query as third word, key is the third, but key is first and the key is the sixth word. Now, when I am doing inner products, all of these are calculated parallelly, right, and then I take a weighted combination. So, I just take the V1 times beta T1 plus V2 times beta T2 plus Vt times beta T3 all the way up to V6 times beta T6. I am just taking a weighted combination. Now, if I interchange the first vector embedding and the sixth embedding, that is, if I take the first word and put it in the last word and take the last word and put it in the first word, the sentence is going to look different, right. For somehow let us take an example that there are two sentences where only the first and the last word got switched. Okay. Now, obviously the sentence is different, right, but when I do a processing like this, there is nothing that changes, right. V1 instead of V1 here, now it will become Vt. instead of VT here, it will become V1. That is, that first and last word got interchanged, but nothing. So now because VT is coming here, KT will come here, right? And so since V1 is coming here, K1 will come here. But if you look at the processing, they are just weighted combination. So instead of adding some quantity plus some quantity plus some quantity plus the last quantity, now I am changing the last quantity plus this plus first quantity. The total sum will not change, right? So if I interchange two words also, the effect is 0. I mean, there is no change in the vector, that is, it is insensitive to the word order, right. So similarly, I garble these words also, I will get the same thing, which is not good, right, because we want to maintain that one word came before the other word, and that should also play a role, right. So to do that, they introduced, so Vaswani and these guys introduced something called positional encoding, okay. This encoding is just a vector that is added to each word. So like first position, I give one vector, like 1 hot, second position, third, I mean I can give 1 hot or anything that I want. Normally they do something called sinusoidal positional encoding or something like that, but do not worry. So there is a unique for the first, for the second, for the third, you give some unique vector, right, and therefore when it is the first word, I will add the first an identity or a vector that says that this belongs to the first place. When it is in the third position, I add a vector to it to indicate that it is in the third position. When it is in the sixth place, I will add a vector to it in the sixth position. So now if I interchange V1 and V6, the last one and the first one, the position encoding will change, because now the last word which was in one sentence now becomes the first word. Even though the V1s, the embeddings remain same, the positional encoding has changed. So therefore the vector will change. Therefore once the position encoding is added, the vector is different. So these two vectors will become different. Therefore the output will be different just because I have changed the words. So that way we are able to capture that, I can't just garble the words. I need them in a certain order. Okay. So these are the only 2 or 3 important points that are useful to remember for a transformer. One is we can parallelize. Second is self attention, which is very, very beautiful, that it however far, however close, they all have influence on every word, right. Every word influences every other word, which is very beautiful, and not through some hoops, through all this hidden layers and all, like the recurrent neural networks. It is direct. How similar are you to me? Okay, that is all. It's directly looking at it, right. And third is that because of this way we have constructed the self attention, we have to be careful to indicate which word occurred first, which word occurred second, so that if I interchange, the positional encoding will capture the change, and therefore the outputs also will start changing. Okay. So 3 broad ideas, that 3 broad differences that are very important for self attention. Okay.